Okay, copy that. Thank you.
Absolutely.
So, first things first, I wanted to welcome everyone to GrimmCon. Thanks for having me. And my name's Jason, and I'll be presenting on a PKI primer and a lessons learned. So this is not meant to be too terribly in depth. So if there's anything that doesn't make any sense, please let me know, and we can go ahead and just dive right on in if everybody's okay with that. So first things first, intro and disclaimers. This is meant to be a primer on PKI. The talk is geared towards identifying ways that we use PKI in our daily life and helping us to understand how we use it, how we utilize it, where it's at, all that fun stuff. I am by no means an expert. I'm happy to share what little information I have. If you have questions, please feel free to ask them. This presentation is my own. It's not a reflection on any employer's past, present, or future. And if I have any information incorrect, please let me know and I can get it fixed. So without further ado, we'll go ahead and jump right in. So first things first, I kind of wanted to start out with giving items that we use PKI in. One of the most common uses that most folks don't recognize is that we do use NAC. PKI is used in NAC. NAC is Network Access Control. What we do with it is we use PKI to authenticate the device to the wired or wireless networks. You'll hear it called 802.1x authentication, network access control. Those are the exact same thing. So 802.1x authentication is going to leverage a PKI to get a client, a device onto the wire or wireless connection. We use it for checking and authorizing applications, specifically code signing. So when you run that new application on your computer for the first time, it's usually authored and signed by some PKI at some point in its development process. And one of the things that's becoming more common is adversaries are going to start putting certificates in their malware code so that they can emulate that and get on through. That's one of the big attack vectors that we are always concerned with when we see new PKIs coming to fruition. We use it in protection of user data using encrypted file systems. What we typically do is we'll put a certificate on the device and we'll use that to encrypt the hard disk drive so that, or solid state drive or whatever it might be in that system so that we can protect that information on that device. We use it in protection of IPsec, Internet Protocol Security tunnels, and VPNs, virtual private network tunnels. We use it for encrypting that communication from point A to point B as a protection mechanism. For LDAP query protections, whenever your lightweight directory access protocol, we use it for protecting that. We use it for two-factor authentication when we're using smart cards. There's a little bit more to that, and we'll get into that a little bit later in the presentation. The call out there is that we have certificates and keys that we put into the key store on the smart card, and we use that when we're doing authentication for things. We use it for protecting traffic whenever we go to third-party sites using SSL TLS. Quick caveat there, if your site's still using SSL, might be time to upgrade to a TLS. I don't know many that are still using SSL, and there's good reason because it's very insecure. So keep that in mind, but we use it all the time in our normal day-to-day browsing. Every time you see that padlock next to your HTTPS connection, you're going to be using an encryption, using PKI to do that encryption.
SSL is insecure, so we don't want to badmouth it or it'll feel bad, right? Is that what I'm hearing?
I think it can handle it. Anything less than SSL v3 at this point is considered largely compromised. So really would advocate anything TLS 1.2 or 1.3, or if you can swing it, only enforcing that. But realistically, a lot of those cipher suites that are exposed in SSL v3, we don't see as secure anymore. And good call out. Thank you, Matt. Implementation of secure email. We use it for signing and encrypting emails all the time. I'm not going to go too deep into that, but suffice it to say, we use it for a lot of things. So wanted to go ahead and get started in the meat of the presentation. So what exactly is PKI? we want to take a moment to define what it actually is. So PKI, Public Key Infrastructure, is what the acronym stands for. It's the key word there is infrastructure. It's a set of things that we use to deliver content to a endpoint or individual, okay? So we can go into a lot of the nitty gritties as we go through the presentation. If there's anything that doesn't make sense, please ask the questions. The big call out here is, like any other infrastructure within IT, there's a lot of different pieces of it. We need a location or a protocol to validate certificates. The way that we can do that is through one of two mechanisms. We can either use CRILs, certificate revocation lists, or we can use OCSP, Online Certificate Status Protocol, okay? Two are not mutually exclusive. What the big call outs and caveats are is OCSP, what it does is it is a query and response. The cool thing about OCSP versus a CRIL is that response that comes back from the, and many times it's the issuing CA that's actually responding to you, or an intermediary CA, but we'll get into that stuff later. But that Online Certificate Status Protocol response is signed, which is the nice part. Unlike with a CRIL, which is just a straight pull down, and then you're depending upon whatever encryption and transport mechanisms are already there. So the cool thing about OCSP is it's a much, much smaller piece because of the fact that it's only having to respond for that one certificate, whereas a CRIL is everything that's been published against that CA, and you have to parse through that thing before you can even find if the certificate's valid or not. So from the standpoint of timeliness and small packet transmission, you're going to want to choose OCSP if that's a consideration. The other call out that we have to speak to is, as part of that infrastructure, there's these things called certificate templates, and we'll get into it a little bit later when we talk more about what an actual CA is and does. But the certificate templates are what defines whether or not you're going to get a certificate issued from that issuing CA. The caveat and call out there is that depending upon how that certificate template was created, it'll force a lot of your choices and decisions with regards to your issuing and intermediary CAs. So we want to keep that in mind. Like I said, it's just the set of rules that the issuing CA follows when it's giving you a certificate back. So the other call outs as far as considerations with regards to the infrastructure, we want to make sure that we speak to network segmentation. One of the things with regards to why we care is the fact that we want our issuing CAs exposed so that they can get certificates to the requesting party or device, but we don't want them exposed where they're accessible to malicious bad guy trying to get certificates off of our CA. Another consideration that we want to keep in mind is it's exceptionally common to see a Microsoft Active Directory stood up as the underlying operating system of your PKI infrastructure. The call out there is that any of the material weaknesses or insecurities of how you've designed your domain and or how you've designed the underlying OS are going to impact your PKI. And then the last caveat is we want to keep in mind hardware protections, physical protections, what defenses are in place. If we leave this thing sitting in a closet in our office and it's a remote site and there's no security on site and that thing grows legs and walks away, it's very infrequent that you wouldn't have a very large scale issue with your PKI if that server, if it was an issuing CA, went walkabout. So we want to keep all of those things in mind as we go about designing and implementing. So you'll have to bear with me. This is a little bit technical for a couple more minutes and then it starts getting a little bit easier. In order to understand PKI, we have to identify and understand the differences between symmetric versus asymmetric encryption. In symmetric encryption, I'm going from my regular text to a ciphertext and back using the exact same key. So both pieces, same key, whether it's forwards or backwards, same function, right? In asymmetric encryption, which is what PKI is and the entire basis of PKI, you have a public key and you have a private key. And what that translates to is you use one key to go one way and the other key to go back, okay? Let me get a drink here, please.
No alcohol until you're done.
It's water.
Forget it. You can drink all you want.
All right, I like it. So I just created this table. This is just a quick high-level overview, comparing the different components to symmetric versus asymmetric so that you can know which one you got, right? So symmetric, it's just a single key. In asymmetric, it's 2 keys. What happens if your key material is compromised in asymmetric? It's not as much of an issue because of the fact that you have an underlying infrastructure that all of the keys are hosted through, so you can get that information to individuals relatively easily. In a symmetric key scenario, you don't have that luxury because there is no infrastructure in place for it. So you create a key and you give it to your 5 buddies, and then you change that key, you now have to give that back to your 5 buddies. Whereas in an asymmetric, which is a PKI, you would have the ability to change that key, but then because of the PKI, it would send that information out to the people that are using it. How are the keys utilized? Again, this is just reiterating what we talked about on the previous slide. In symmetric, it goes same key material forward to ciphertext and from ciphertext back to plain text. In asymmetric, again, it's I use the private key to encrypt, and then I use the public key to decrypt, or vice versa. It depends on what you're using it for. There's different things that they will do with regards to how it's being utilized as to how the keys are used. For the example that I'd like to present, it's if I'm sending you an email and you want to be able to verify that it indeed came from me, what I'm going to do is I'm going to sign that email with my private side, and I'm going to depend upon you getting my public side of my key from PKI to validate that it is indeed me that sent you this thing. Okay. Key distribution synchronization requirements with regards to symmetric, yes, it is absolutely required. If you'll remember the example we just talked about, if I send it to 5 people, I'm responsible for maintaining that key material for those 5 people. In asymmetric, it's not. The other call out as to why would I have 2 of these if this asymmetric is sounding so much better, right? So the call out there is symmetric is lightweight. It goes forward and back real quick. Asymmetric, on the other hand, is computationally heavy, which means it loads a processor more. So depending upon what cipher suite and algorithm and all the fun stuff, it can be medium to heavy load on a proc. So the reason that we do this is what's typically going on when you have a TLS session is it does bulk encryption via a symmetric key, but then it uses asymmetric to encrypt that symmetric key material inside of that session. So those are the 2 use cases that we typically see it deployed in. So I wanted to dig into now what exactly a certificate is. So when we talk about certificates and you hear somebody say, oh, I've got a certificate, they're typically referring to an X509 certificate from RFC 5280, typically. RFCs 2459, 3280, and 3647 have existed prior and still exists. It's important to call out IETF, Internet Engineering Task Force, doesn't revoke stuff. They just supersede it, and that's exactly what happened with 5280. So it defines the new what we do within certificates. But as it's part of its history, 2459, 3280, and 3647 have all been defining components to it in the past. At the core of what is a certificate, it's simply an asymmetric key pair signed by a certificate authority from a valid CSR, and we'll get into that. A CSR is a certificate signing request. It's important to call out when you actually request a certificate, when you generate that CSR, you've actually already got your key pair sitting local at your workstation or wherever it was that you generated that. And the reason that we call that out is because it's important to protect your key material. So if you generate that thing at your local workstation gets popped and your key material is sitting there, it's potentially a bad situation to be in because you've already got your private key there. So we just want to call that out as something to be aware of and be concerned with. So in order to understand how certificates work, we have to kind of talk about this concept of certificate chaining. Certificate chaining is simply validating all of the hops between your issued CA, or between your issued certificate and all of the levels of CA that it came through. So we typically talk about a 3-tier architecture, which I'll get to in just a minute, as to how we protect and secure the thing. But it's important to call out that as part of that certificate chaining, I have to validate every step of the certificate. So I go from my root offline CA to my intermediary offline CA to my issuing CA, and all of those things have to validate and check out before I can say, yep, the certificate that I got from my issuing CA is valid and safe, and I can use it, and there's no issues. The call outs there, pardon me one second. The call out there is that your periods of validity matter. Typically, when you see an offline root CA, you'll see a really long time period of validity for it because they don't want to take that thing down and redo the entire certificate chain. So you'll see long time frames of period of validity on the certificate for a root CA. You'll see it go down and down on the different layers. So you'll see, for example, a 15-year period of validity for your root CA, and then you'll see only a 5-year period for your intermediary CA, and then you'll only see a year period for your issuing CA as an example. The other call out here is that the cipher suite selection when you're generating those certificates matters. The reason being, you'll hear about SHA-1 versus SHA-2 as an example, that SHA-1 algorithm is largely considered antiquated, we'll call it, and as a direct result of that, a lot of the PKI has to be reissued with a new hashing algorithm being used. So it's important to make those considerations when you're standing it up. I would not advocate using SHA-1 on a new CA if you're just now standing it up. SHA-2 or greater, if you can run it, would be much preferred and recommended. You heard me mention earlier a key store, and what we need to talk about, the key store in a smart card versus the key store in an operating system versus a key store in a browser, they all behave and function differently. What you want to be aware of is this is basically the digital lockbox that your certificate or key material sits inside of. The call out here is that the protection of this material is largely dependent upon the implementation. So what smart cards have been typically used for, you may have seen DoD cards floating around, those are smart cards. And what they typically have is a certificate store that contains a bunch of different certificates inside of it, excuse me, with a mechanism to authenticate to that key store so that you can get at the content inside of it. And what I've got here as far as all the images are concerned are talking about the ways to interface with the integrated circuit that makes up a smart card and get at the key store. So you'll see the pinouts on there. You'll see how it's actually designed, which is kind of cool. And there's a lot of different functions, features as part of those certificate or as part of those smart cards, excuse me. So in order to kind of understand, we talked a little bit about what a certificate is. Again, recall back that it's basically just an asymmetric key pair, right? An X509 formatted asymmetric key pair. What we want to talk about now are what are the different types of file formats I'd see key material in. You hear me talking about key material. Key material is all the stuff that surrounds and deals with how a certificate is, what it does, what it functions as, all that fun stuff. What I wanted to talk about is a couple of big caveats and callouts here. So I'm not going to read the slide to you. There's a P12 is the one that I would be concerned with. So you'll notice when you read the descriptions there, the P12 is the only one that contains private key material. So the reason that I'm saying to be concerned with that one is because of all of the file types, that's the one that actually contains something relatively sensitive. So that private key is typically designed and intended to never exit out of the key store. The P12, with the way that it functions and why it does what it does, it's designed to make that certificate portable, to move it from position A to position B, wherever that might be. When you're generating that P12 file, it's going to prompt you to create a strong password because you have to have a password in it. And the reason that you have to have the password is because they understand that this thing is dangerous and sensitive. So we want to make sure we control it and keep it safe. Another call out here, you'll see the CRL. That's the certificate revocation list file extension. That one is just like I mentioned earlier, that is the file format that you'll see, and it's not encrypted, you'll note, it's encoded. And the call out there is that encryption actually does something, whereas encoding does nothing, it's reversible. So what we want to make sure of is that when we're moving these things from point A to point B, we protect them, we keep them secure. A certificate chain isn't super sensitive. I would say to keep it safe, but with the fact that it's only got the public keys and not the private keys, it's relatively safe. But again, it's encoded, not encrypted, so this stuff can identify to an adversary what your PKI looks like, which might be detrimental. So you want to keep that in mind. One second. We need to speak a little bit about certificate structure at this point. The call out here is that versions 1, 2, and 3 are all building upon one another. Version 2 works, all version 1 fields work in version 2. All version 1 fields work in version 3, but not all of the version 3 fields are going to be available in version 1. Specifically, you'll see that extensions field is only available in version 3. What they've done is over the years, they've increased the functionality of what a certificate is based upon its version. But again, it's important to call out that version 3 encompasses everything from versions 2 and 1. So it's backwards compatible legacy functionality is all going to be there. The caveat there is that version 3 is what you'll see issued. You will very rarely see a version 1 or a version 2 issued because it doesn't make any sense. This next slide, I wanted to speak about how you actually go about getting a certificate. So you heard me mention earlier that you generate a CSR, a certificate signing request. So what you actually do is you generate a public and a private key pair, and you send it up to that issuing CA. That issuing CA takes a look at its certificate template and says, yep, you've got all the information in here that you need, and it generates a certificate back to you. The way that it does that is it actually signs the CSR with its certificate and gives you the response back. In a typical deployment for a issuing CA, you'll have a pickup location that you can then retrieve that key material at to pull it down and put it into your certificate store, or key store, excuse me. The important call out here, again, when you generate that CSR, you've already got that public-private key pair in a key store typically, and you'll want to import it back in. So how PKI works is I have to generate the CSR, to get the certificate back, and then I import that into my key store. But the call out here is that key material that you used, if it wasn't protected by that key store, is now potentially going to be great intel for an adversary. So we want to make sure that we either purge it, we escrow it, or we do some sort of offline backup somewhere else, okay? So you've heard me say CA about probably 30 times now. Certificate authority are the parts of PKI that actually make the entire system function. They are the component that you go to get your certificate. They typically have mechanisms in place for how to go about retrieving a certificate. They also sometimes will have functionality that allow you to edit a CSR, add it before you issue that certificate for it. And they give you all the administrative overhead functiony type things that you do to certificates that you're generating from your PKI. The recommendation and the call out here is that when it comes to your issuing CAs, especially, as well as every other level of CA, and we're going to talk about 3-tiered that I spoke about earlier in just a minute here. But the important thing to keep in mind is that your PKI is only ever as strong as you can defend it. So you need to make sure that you've got hardware security modules, trusted platform modules, all of the fun hardware-y things that us geeks love to play with. A hardware security module versus a TPM, if you'll pardon me, I'll quickly explain what the difference is. The hardware security module, that thing has protections in place so that it's got key material inside of it. The caveat or the call out, so to speak, from that versus a TPM is a TPM stores it securely, an HSM stores it securely, but it's also got tampering protections in place, meaning if I see somebody trying to get my key material out of my HSM, it's going to auto-destruct that material in a lot of instances. It's going to send an alert off to my security operations center. It's going to alert all of the PKI admins. There are specific things that HSM, that hardware security module, are going to do versus a trusted platform module is strictly passive. So it's going to hold that material, but it's not going to necessarily do anything to protect it or to alert you to the fact that it's attempted to be compromised. You heard me mention a three-tier architecture, and like I said, we're going to talk about that just next. The call out is that your issuing CA is the entry point to pretty much all attacks. You want to lock down the rest of your infrastructure so that only the issuing CA is the thing that's exposed, and people are talking to that via whatever process you've defined. So what we want to make sure of is that that exposure is only for that issuing CA, and that we've hardened it as much as we can to keep it secure. Again, you've heard me mention three-tiered architecture a couple of times now. So I wanted to point out a couple of quick questions. Why do you want to keep your offline? Why do you want to keep your root CA offline? Why do you want to keep your intermediary CAs offline? What protections should I put on them? All that stuff. And the simple answer for that question is you want to put all the protection mechanisms on them that you can. You want to have a SIM collecting intel from all of your different log sources, from all of your different functions that your CA is doing. You want to make sure that your devices are as much offline as you can have them. The reason being, it's kind of hard to attack something that's not on. What you do is you stand up your root CA. We have to talk about a self-signed certificate. What that means is I stand up my initial root CA as a self-signed certificate. I generate a key pair, I generate a certificate, and it's self-signed, meaning it's not signed by something else, because again, we're building that infrastructure out. So that self-signed certificate of your root CA is trusted because you said to trust it. You then implement your intermediary CAs using that root CA's certificate to sign it, and then you take it offline. So now you've got the first node of your tree and it branches out. So you've got root with a whole bunch of intermediaries with a whole bunch of issuing CAs. And the reason that we keep them, like I said, offline is because it's a little bit difficult to attack something that you can't log into. And then your issuing CAs down here, like I said, doing all the real work. Now, has anybody heard of DigiNotar? It's real uncommon. The reason that you haven't heard of them is because they no longer exist. They were a big time CA, PKI back in the day, specifically back around 2011, I believe, is when they were breached. And then they went bankrupt in 2012. The callouts there, they were issuing certificates for Dutch government, big businesses all over the place. And as a direct result of them getting PKI wrong, they are no longer in business as the call out. What ended up happening is there was a singular adversary, one criminal, that took credit for the attacks. I believe they prosecuted, I can't recall on that aspect, so I'm sorry, but I don't remember. They were in the systems for about 6 weeks before they were detected. It's important to call out normal dwell time is something like 6 months right now. So they did a fantastic job of detecting it, but even detecting them quickly didn't save them. What ended up happening because of this adversary, this criminal, they got in and they compromised all 8 machines that were their issuing CAs, and all 8 of them being compromised meant that the adversary could do whatever they wanted. They issued certificates for domains that they didn't own. They had all sorts of stuff going on that was bad. One of the callouts here is they didn't have great security controls. So they didn't have off-box security logging. So what ended up happening is adversary compromised intermediary CAs, or excuse me, issuing CAs. And because they didn't have off-box logging, they didn't have anywhere to go to look at the logs to figure out just how bad the problem was. So they had to assume, oh goodness, it's been everything. So it turned into a really nasty investigation. The initial breach, the other call out is the initial breach was a web server that was popped that the adversary then laterally traversed deeper into the network. And had they actually done a better job of network segmentation validation and enforcing it, they wouldn't have been in the predicament that they were in. So adversary got on got a web shell, pretty similar. They then laterally traversed inside and were able to compromise issuing CAs. And again, the call out here is they don't exist anymore. They tried and they didn't get it right, and they're no longer around. So that's pretty much the end of my talk. Thank you for attending. I appreciate your time. I hope you learned something. If you didn't, I apologize. And that's my Twitter handle, and you can feel free to talk to me about any questions or comments.
Hey, Jason. So let's see. You got a few comments here.
Okay.
Obviously, several people saying excellent presentation. I saw that both in the Q&A and I saw it on Discord. So thank you very much. You clearly had your poop in a group. I appreciate that a lot. Good emphasis on the fact that compliance is not security. Let's see. Love the slides. Yeah. Let's see. Nope, just good comments. So thank you very much. Really appreciate it. You had a lot of details on a very difficult topic. I used to run the CA, or actually I created the CA for a large multinational a number of years ago, and I was surprised at, well, once I understood the concepts, I was surprised at how simple the details were. You kind of had to type in a lot of things or copy and paste, but the details of actually running your own CA were relatively easy once I figured out the details of how to think about things. So thank you for bringing it down to a mortal's level. I appreciate that a great deal. So what's next for you? You've got another talk scheduled. COVID-19 changing your plans a bit?
No talks scheduled later in the year. Who knows? Maybe I'll sign up for another one. I'm a glutton for punishment, so. Good. I'm glad that it went good. If anybody's got any questions, like I said, I'm on Twitter. I'm happy to talk about it. And
Jason, you're also going to be in Discord channel for a little while, right?
Yes, sir. Yep. In there, I'm Reaper, Romeo 3-4, Papa Echo, or Papa 3 Romeo. Sorry.
Nice. All right.
Real quick, I find it funny that you said that it's dead simple. PKI is simple. It's all the other stuff that's hard. Certificate lifecycle management and a supplicant and how you actually go about implementing 802.1x, all that stuff is difficult, but it's not the PKI that's hard. That's the easy part, unfortunately.
Right.
Escrowing and everything else bites you in the butt usually.
So much of the technology has already been created and has been pretty well thought out. Mm-hmm. Once you understand the concepts are actually quite a bit easier to understand than what we make of it. It's that initial ramp up to learning. These are brand new concepts to most people in IT. Most people they've never needed to know, they've never wanted to know, and it's really scary getting that initial ramp up.
Absolutely.
Once you're there, yeah, no, the technology and managing. What I find also very difficult is communicating to a non-technical person or even a lot of people in technology that have never wanted to learn this stuff, the impacts and how things can go badly when PKI is not rolled out, when it's not rolled out well. When your APs don't know to check, or your apps, when your apps don't know to check that the CA is trusted, that the intermediaries are trusted. Oh, that the intermediaries are signed by a trusted CA. The whole certificate chain, that stuff, that's not the easy part, but You know, when you
Absolutely.
understand it,
Absolutely.
it's a new concept. Anyway, thank you so much. Oh wait, let's see. Yep, nope, just more of the same. Thank you, Red Top Reaper. PKI is a tough topic. Yeah, thanks, Kate. Exactly. Very well done. See you in Discord.
Thank you, sir. Yes, sir.
Yes, we will get a slide up, and then we'll be starting our next speaker in about 12 minutes.
Copy that.